Welcome. Our EE2FH3 project is on multiband folded loop antennas for smartphones. However, the purpose of this video is to provide a brief introduction to small antennas as a whole. This presentation is by Aditya, Brandon, Arvin, and Ali. Let's get started. Firstly, we'll provide a brief overview of transceivers, which are often paired with antennas. A transceiver is a device that turns electrical signals into radio waves and vice versa. It consists of both a transmitter and a receiver, hence the name. The transmitter converts electrical signals into radio waves, while the receiver has the inverse function of converting radio waves into electrical signals. Transceivers are paired with antennas to transmit and receive the signals as radio waves. Some devices where transceivers are used include walkie-talkies and anything with a Bluetooth functionality. A transceiver consists of a transmitter and a receiver, as the name suggests. In the transmitter portion, up here, the control signal is modulated with an oscillator to generate an actual oscillating AC signal. This signal is then amplified, then sent up to the antenna for transmission, over here. In the receiver, the signal comes in as a radio wave, then is converted to an AC signal. The signal is then put through a low noise amplifier, which clears out any ambient noise in the signal, and then amplifies it for further processing. This further processing is done through demodulation, as represented by these filter blocks. Now let's talk about antennas as a whole and introduce the electromagnetic theory behind their operation. Antennas are used to convert AC signals into electromagnetic waves. Alternating current can be seen as a positive and a negative charge, constantly swapping back and forth in space. We have electric field lines that travel from the positive charge to the negative charge. So, as our charges swap back and forth, this creates an oscillation in both magnitude and sign of our electric field. This electric field also has a perpendicular magnetic field, which also oscillates in sign and magnitude. This EM field travels through space as a radio wave, and then can be picked up by other antennas or receivers. This diagram shows a simplified electrical circuit for an antenna. As the wires come off the source, they are bent in opposite directions here and here. This is done so that the electric field made by one portion of the wire is not cancelled out by the electric field in the other portion of the wire. These two portions of the wire, here and here, both have the same current but are pointing in opposite directions, so the fields made will cancel each other out. But when they're traveling in the same direction, they won't. So, based on the right-hand rule, we know that when the current is traveling in the upward direction, the magnetic field will be pointing into the screen. When the oscillation changes and the current is traveling in the opposite direction, the magnetic field will be pointing out of the page, thus creating our alternating magnetic field, which has a perpendicular electric field.
Now that we have a general grasp on antennas, let us look at their operations at different frequencies. Antenna performance rely heavily on their impedance along with the transmission line. Antenna impedance relates the voltage to the current at the input of the antenna. An antenna with a real input impedance, meaning a zero imaginary part, is said to be resonant. Note that the impedance of an antenna will vary with frequency. If the impedance contains a partly imaginary number, it will reflect power back to the source. Let us look at the case where there is low frequency. When we are dealing with low frequencies, the transmission line that connects the transmitter or receiver to the antenna is short. Short in antenna theory always means relative to a wavelength. Hence, 5 meters can be short or very long, depending on what frequency we are operating at. At 60 Hz, the wavelength is about 3,100 miles, so the transmission line can almost always be neglected. However, at 2 GHz, the wavelength is 15 centimeters, so the little length of the line within your cell phone can often be considered a long line. In general, for maximum power to be transferred from the generator to the antenna, the ideal value for the antenna impedance should be the same as the source impedance, and that's observed in this equation on the left-hand side. However, if we design an antenna to match the source impedance, we may still run into a problem within the high frequency domain. In low frequency circuit theory, the wires that connect things don't matter. Once the wires become a significant fraction of a wavelength, they make things very different. In general, the transmission line will transform the impedance of an antenna, making it very difficult to deliver power unless the antenna is matched to the transmission line. The equation for impedance at high frequencies is derived on the right-hand side, but to summarize it, if the antenna is matched to the transmission line, then the input impedance does not depend on the length of the transmission line. This makes things much simpler. If the antenna is not matched, the input impedance will vary widely with the length of the transmission line. And if the input impedance isn't well matched to the source impedance, not very much power will be delivered to the antenna. This power ends up being reflected back to the generator, which can be a huge problem, especially if high power is delivered back. This is known as impedance mismatch. Let's give two examples to summarize that previous slide. In example 1, let's say we plug a vacuum cleaner into a wall outlet. The cord, transmission line, that connects the power to the motor is 10 meters long. The power is supplied at 60 Hz. The wavelength at 60 Hz is 5,000 kilometers long. Hence, the transmission line in this case is about 0.00002 wavelengths. As a result, the transmission line is very short relative to a wavelength and therefore will not have much impact on the device. However, in example 2, suppose a wireless device is transmitting at 4 GHz. Suppose also that a receiver is connected to a microstrip antenna via a microstrip transmission line that is 2.5 centimeters long. The wavelength at 4 GHz is 7.5 centimeters. Hence, the transmission line is 0.33 wavelengths long. Since this is a significant fraction of the wavelength, 33%, the length of the line must be taken into account in analyzing the receiver/transmission line antenna system. As a designer, we must avoid this mismatch at interest of frequencies. This is known as impedance matching. Impedance matching is the process of removing mismatch loss. That is, we want to minimize the reflection coefficient to reduce the power reflected from the load. I mean the antenna. We also want to maximize the power delivered to the antenna. To achieve perfect matching, we want the antenna or load impedance to match a transmission line. We use the term reflection coefficient to represent impedance mismatch. Ideally, if there is a perfect matching, then the resultant reflection coefficient will be 0. In cases where we are not interested in the bandwidth frequencies, then the reflection coefficient will need to be large. We will now look at the different types of small antennas very briefly. A patch antenna is a low-profile antenna which is mounted to flat surfaces. It consists of a flat rectangular patch of metal over a larger sheet of metal called a ground plane. Two metal sheets together form a resonant piece of microstrip called a transmission line. This microstrip transmission line has length equal to half of the wavelength of transmission. These two metal plates also behave like a dielectric, and the distance between the two determines the bandwidth of the signal.
Another antenna is the planar F antenna, or PIFA, which is similar to an inverted F antenna. The PIFA is popular because of its small size and omnidirectional radiation pattern. The resonant frequency is controlled by the dimensions of the patch and resonates at quarter frequencies. The planar inverted antenna is characterized by a shorting pin that connects the patch to the ground plane. At high frequencies, the shorting pin can be used to control the impedance of the antenna by introducing a parallel inductance, which will change the resonant frequency. Loop antennas are circular in shape and are often used as receivers because they have poor transmission properties. This is because they have a low radiation resistance and high reactance, making it difficult to match their impedance in a transmitter. Loop antennas are usually used in implants because they are relatively unaffected by the body. Electric fields are usually distorted by the body because the body has a high permittivity constant, but loop antennas generate strong magnetic fields that can cause radiation, which the body does not distort as much as electric fields.
So now let's talk about how these antennas can be used in smartphones to allow for communication. So different countries operate on different frequencies. What does this mean? In order to communicate using, say, a smartphone in that country, your smartphone must be able to operate on that specific frequency that their cell phone towers are using. The North American region primarily operates on 2 frequencies for mobile communication. The rest of the world, that is Europe, Asia, and the Middle East, will operate on 2 different frequencies. In order to allow for international mobile communication, the device must be able to operate on all 4 frequency bands. If you switch frequency bands, you'll be considered roaming. So different bands have different purposes. The frequency bands mentioned above are referred to as 2G bands and are primarily used for communication, that is, talking and texting. There is another band that exists at a higher frequency, specifically around the 2000 plus MHz range, which is called 3G. In this range, data transfer rates are faster, which allow users to have access to internet while on the go. This will allow you to surf the web, use video calling, or even watch TV. So this image here just gives a graphical representation of how you would want the antenna in your smartphone to work. Ideally, what you want is your antenna to operate within bands above this dashed line here. So for example, these areas here, here, and here. And you would also want to reject anything coming from unnecessary frequency bands. When you design your antenna, you can change the physical parameters that will allow you to optimize this blue line in order to accept or reject specific frequencies, depending on the application of the device. So again, this part of the world here will operate on 2 frequency bands, and this part of the world here will operate on 2 different frequency bands. And here's just a summary of the different frequency bands that are used and in what regions they are used in. GSM 850 and DCS 1800 are used in the North American region, so mostly in Canada and the United States, but it also extends to the Caribbean and Latin America. EGSM 900 and PCS 1900 are used in Europe, the Middle East, Africa, and the Asian Pacific region. You might be wondering why there are 2 different frequency bands per region. One band, typically the higher frequency band, is used more frequently, whereas the lower frequency band is used as a fallback in case the other fails. The last column is just a number that designates what frequency band is being used. Instead of saying, for example, that a certain cell phone company operates in the 850 and 1800 MHz frequency range, you could just say that they run on band 3 and 5.
Specific absorption rate, or SAR for short, is a measure of how transmitted RF energy is absorbed by human tissue. SAR is critical to antenna design, because if the SAR is too high, the antenna must be changed. Typically, if the SAR is too high, the transmit power is lowered. However, since there is the minimum transmit power specifications for mobile devices, the SAR cannot be dropped indefinitely. As a result, the antenna positioning is critical. The antennas for mobile phones are typically on the bottom of the phone to keep the radiating part of the phone as far as possible from the brain region. Other methods for dropping the SAR include impedance matching, which was brought up earlier in the presentation. To conclude on this presentation, while there are a variety of small antennas and the uses for them may be different, the main concern for implementing them onto smartphone devices looks at 3 things. The first being that it has to have the appropriate reflection coefficient to incorporate the desired bandwidth frequencies. Second, the size of the antenna itself must be able to incorporate into the smartphone. Lastly, the theory behind the small antenna must be feasible in both the uses of materials as well as the cost for the client. That concludes this general overview on small antennas and their purposes for smartphone devices. Thank you for listening. This slide contains our references.